Good morning. This example is to illustrate how to get SAS to compute an analysis of variance for you. The text of the problem is repeated here for our convenience. 15 1-acre plots are used to compare yields of 3 varieties of wheat. Each variety is assigned to 5 randomly selected plots. At harvest time, the yield measured in bushels per acre is obtained. During the season, 3 plots were flooded and all wheat was lost from those plots. Now the concepts here from the experimental design standpoint of when it says 5 randomly selected plots, if the plots are selected at random, the implication then is that they are independent of each other. So that the plots assigned to variety 1 are independent of those assigned to variety 2 are independent of those assigned to variety 3. That's what makes this a completely randomized design. Okay. Now then, the 3 that were lost due to flood, 2 of them look as though they belong to variety 1, and a single plot was lost due to flooding in variety 3. So we need to be able to communicate in our program what the variety is and what the responses for each of those varieties are. And so this is how we do this in the programming. Okay. Now, just a note about the templates that I give you for the programs. Anything that is uppercase is a SAS command. Do not change how it is spelled or punctuated. Blank lines in your programs are okay. Don't cause a problem. They just give a kind of a visual separation for pieces of code. Now, to create the data set that contains the varieties of wheat and their yield responses, we have used the data, input, data lines, those 3 statements in that order. The data set we name wheat, one word. Anything that's lowercase you can change to make problem specific. The exception here is on the input statement. I used variety with a capital V and yield with a capital Y. There's a case sensitivity in the input statement, and I wanted that variety and yield to be title case on my output. If I spelled variety with a lowercase v and yield with a lowercase y, that they would look that way in the output. We'll see shortly. But the bigger issue then here, when I write on the input statement, I'm telling SAS that I have 2 columns of information, one for variety and one for yield. Variety takes the values 1, 2, and 3, and yield 36, 57, and 50. So by using this double trailing at symbol, it reads across. Otherwise, on each line after the data lines, it reads only 2 pieces of information, and it would only read those first 3 here. If you want it to read across, the at will come across. So, and you have to repeat each variable so that it would be variety, yield, variety, yield, variety, yield, and so forth for all of these other measures. You can't just enter variety once and then list all of the yield responses. It has to be 2 pieces of information for everything up in the table. So it's variety 1, observation 36 here, variety 1, 33. Okay, so each one of these yields has the variety attached to it. On a line by itself, after you enter your data, is a semicolon. The punctuation in SAS is a semicolon, and so that if you put it on the line with your data, it wants to try to read that as a SAS command, which it is not. You own the data, SAS owns everything else. It's a quick way to think about that. Okay. Once we have that information entered, then we want to conduct our analysis. So in our analysis, then we run procglm. The acronym GLM stands for General Linear Model, so that we want to look at an analysis of variance table. And we tell it on which data set we wish to operate. So we want to run the GLM procedure on data set wheat. Proc is SAS's shorthand for procedure. So we say GLM procedure, or some people would say procglm. Then with procglm, at a minimum I need 3 lines of code: procglm, class, and model. Those 3 lines will give me an analysis of variance table. In the class statement, I use the variable or the column from up here that identifies the groups to be compared, or treatment. In the model statement, I write the response equals treatment. Always in that order. Response equals treatment. Up here our treatments were numerical values 1, 2, and 3, and so if we would have flipped those around, variety equals yield, we'll get output, but it won't make any sense whatsoever. Okay, so it has to be response equals treatment. If we would have had more than one response, and in practice we could put those to the left of the equal sign here, and it would generate an analysis of variance table for each response variable. Okay, so for those three lines, ProcGLM, class, and model, we'll look at the output. We'll come back to those other statements shortly. So on page 2 of your handout, then you have the information from the class statement. So it identifies your class variable variety, how many levels it has, and what those levels are. If you see a value here if you typed a 4 instead of a 3 accidentally, that's going to throw off your number of classifications. So that gives you a chance to proofread your data. You also always know how much data that you've measured, so that whenever you come up with 12 responses, that's correct. Had we not used the double trailing at, we would have only had 3 responses. So take an additional opportunity then to proofread your data here on this page. For the model statement, it generates an analysis of variance table for each of the dependent variables or response variables in the data. So at the top of this analysis of variance table, we see that the response variable yield is measured. We have a model with 2 degrees of freedom, error degrees of freedom 9, and total degrees of freedom 11. These correspond to number of varieties minus 1, the grand sample size 12 minus the number of varieties 3, and grand sample size minus 1. The other thing that we notice here is that the model line is exactly the same as the type 1 analysis and the type 3 analysis. I want you to get in the habit of reading the type 3 analysis. We are going to look at models that get more complicated than this one. And when they do get more complicated, this model up here in the ANOVA table, this line stays simple, it's just a model, but these two tables have more information in them, and in particular the type 3 analysis is what we're looking for. So here the type 3 analysis is the simultaneous comparisons of these 3 means. As always, you want to be able to write a conclusion, and so if you're a 0.05 person, a strict 0.05 person here, you would find that there is no evidence that the 3 varieties of wheat differ in mean yield. Cite alpha. The F statistic with 2 and 9 degrees of freedom of 4.11, it's this 2 degrees of freedom and the error degrees of freedom and the computed value. It's printed the p-value for you, so you don't need to go look anything up in a reference table. It's already given you that information here. At the bottom of the page is a box plot, and inside this box plot then it contains the analysis of variance F test and p-value, and this is the result of the model statement. So it gives me a box plot for each variety, variety 1, variety 2, and variety 3. Variety 1 only had 3 observations, so we don't see any whiskers here like we do on the others when we get small sample sizes. The means for each of the groups are represented by the diamonds inside here. The medians of the observations are these horizontal lines across the box. And so this gives us a quick visual on how the means compare to each other. If we see a significant difference, and we did not, if we see a significant difference, we get some feel for perhaps the largest or the smallest. And so as you get more and more levels to a classification variable, this plot could be very helpful. Now, when we entered our data here, our varieties 1, 2, and 3, we told it there were only to expect only 2 columns on the line after data lines, and we can control that with the double trailing at. But the other thing we could have done, for those who are more familiar, perhaps we have varieties of wheat that are commonly seen in Oklahoma, such as varieties Iba, Tam, and Jag, or these are shortened names for wheat varieties, and so that if I wanted to use those names instead of 1, 2, and 3, I could do that. And to do that, on the input statement, I follow the variety with a space and a $sign. That means variety is going to take character or text values. It assumes, SAS assumes that your variables are numeric unless you say otherwise. So this is the only place you'd ever have to use that $sign is in the input statement. So IBA, TAM, and JAG. If you do have one of your text variables that's longer, say it's use Jagger instead, I would put Jagger first because it tends to truncate, or let the one you enter first determine the length of the text it's going to allow there. But you can put those text values in for the variety. Just please use only one word, no spaces. So if it was a two-name variety, you'd have to leave that out if it took 2 words, because the space in between the two text units would register as going on to read a value for yield. So you want to make sure the yield is numeric, and variety here could have been text. What would change on your class statement is you'd still have 3 varieties, but your values would be listed here in alphabetical order, and instead of the values 1, 2, and 3. Whoops. Back up here, forgot to do something. The mean statement and the least squares mean statement. Okay, those are the next 2 things. So after you compute an analysis of variance, you also want to know, well, what are the means for each of the groups? So the syntax here is means for treatment. So just treatment, or least squares means for treatment. So whatever is on the right hand side of the equal sign, that's what comes into these 2 statements as well. All right, we have options here: standard error, confidence limits, alpha equals 0.05. And we'll talk about those more specifically on those pages. Additionally, in this block of ProcGLM code, I have a title statement. So the syntax here is title, and then you can put the text for title in quotation marks, either single quotes such as I've used here, or double quotes. Just make sure you use a pair, and so that it just labels the output as analysis of variance example, and you'll see that as we page forward. Okay, so now let's look at what happens with this mean statement here. So this would be page 4. This analysis of variance example in this shaded box, that's the result of the title that I used, and it's going to, on each page of the output, that carries through. The mean statement produces an ODS graphic too, and that's this box plot. Notice it doesn't have the analysis of variance f-test inset in any one of the corners. This ODS graph, ODS stands for Output Delivery System, so this is the box plot. It looks just the same as the one before, with the exception of the analysis of variance f statistic. So the mean statement wants to draw one of these 2. The mean statement also produces a table such as this. This table gives me the level of the treatment variable, the sample size for each of those, the y-bar values. So mark this mean as y-bar, 39, 51, 45, and standard deviation. In lecture we call these lowercase s with subscript I. These are standard deviations, not standard errors of the means. So in addition to the means, we could look at least squares means, so LS mean variety, and so that generates this page 5 of results. The least squares means are the same as the sample means in a completely randomized design with this one treatment variety. We'll do more things later on when the least squares means and the sample means are not the same, and if they ever differ, you use the least squares means. That's the preferred computation to use. Now then, we included the standard error option on the least squares mean statement in the program so that it would compute the standard errors for the mean. So the standard error of the mean, remember, is going to be the square root of the mean square error divided by the square root sample size. You may want to write that on here. So we get the least squares mean, which these are the same as the sample means at this time, the standard errors for each of those means, and then we have this p-value, probability greater than absolute t. So it's a p-value, or observed significance level, for a hypothesis test. It's testing whether or not the associated mean for the variety is equal to 0, or is it something different? So variety 1, is the mean yield equal to 0, or is it something different than 0? Well, of course, these are all going to be highly significant because crop yields are positive. If you would have measured, say, what is the change in yield or a change in temperature, something where you could end up with positive and negative values, then it makes sense to examine that test of significance, and these p-values become meaningful. But here in this application, they're just not meaningful. The other option we put on that LS mean statement was CL. CL stands for confidence limits. So CL and alpha equals 0.05. So that gives us the least squares means and then the confidence limits, CL and 95% confidence limits. So the default setting is 0.05. So if I would have just put CL, I still would have gotten 95% confidence limits. If I want 90%, then the alpha option, I'd have to change that to 0.01. If I wanted 90%, alpha equals 0.1, etc. So you can change that, and then it'll change this heading appropriately as well. The least squares means also generates this ODS graph called a mean plot. It's just got 3 little dots on it. It doesn't look highly informative here. There are some applications that we look at later where these mean plots produced by the LS mean statement might be a little bit more informative than this one. If you didn't want any of the plots, you can use an option, plots equals none, and that's on the proc GLM statements. That is, we would go back to the beginning of the program, and after data equals wheat and before the semicolon, you could insert plots equals none, and that would turn off all the plots that SAS wants to generate by default. We'll look at some other ways where we can select which plots we want to include, and so that we don't have to take all of the defaults. We can just be picky about which ones we choose for our results. We have some more information coming up about how do we compare means and some tests there, so we'll look at modifying the syntax on this GLM procedure and the statements within it in upcoming examples. But for now, what you should be clear about is how do I create the data sets, and how do I get an analysis of variance table and generate the sample means, and compute standard errors, confidence intervals, support the calculations that we've learned in the lecture part of the course, because we want to rely more and more on doing things here in SAS. There are a great many things that we're going to do later in the course where we have to be in SAS. We're not going to be able to do the analyses by hand. We want to do it using a statistical software, and we're going to do that using SAS. So you do need to learn how to do this. If you have any questions, please ask. I'm happy to help.